So this is a talk, Ancient Light, and as you can see from the subtitle, it's about imaging a very distant object called a quasar without using a telescope. So this was, in a sense, a lockdown challenge. We all know that the universe is vast, and we all know that the universe is ancient, and large telescopes have imaged galaxies that are billions of light years distant. But I wondered to myself, is it possible to capture an image of one of these very remote objects without using a telescope? And not surprisingly, I wouldn't be giving this talk unless the answer was yes. So there's the first spoiler alert. Yes, it is possible. So here's a publication from 2019 of a group of professional astronomers who surveyed a whole load of quasars. And a quasar is the nucleus of a galaxy that emits enough light to be visible at a distance of many billions of light years. So it's probable that the central engine in any given quasar is a supermassive black hole, and matter falling into the black hole generates enough light and X-rays and ultraviolet to be visible over huge distances. This particular quasar that I had my eye on, this particular publication gave the details of quite a few, and this one I noticed was very remote and should be visible from the UK. Some quasars are only visible from the southern hemisphere. This one I figured would be visible from the northern hemisphere. And this is the spectrum that they obtain. So we have the intensity of light as a function of the wavelength here in angstroms. So we have the blue end of the spectrum and we have the red end of the spectrum. And what's interesting is that feature there, which occurs at about 6,500 angstroms, or 650 nanometers if you prefer. And comparing that with the spectrum from a laboratory-based source which is not moving relative to us, it was realized that this particular feature is actually a transition in hydrogen. It's one of the Lyman lines from n equals 2 to n equals 1. So this peak has been redshifted from where it belongs, which is at 1200 angstroms, and it's been redshifted to 6500 angstroms at the red end of the spectrum. 1200, as you can see from this scale, blue at 4000, red at 7000, you can see that 1200 is way, way, way off to the left-hand side of this spectrum in the ultraviolet. So this peak has been shifted from the ultraviolet all the way through the visible spectrum into the red. So that's a very large redshift, and that indicates that this object is very remote. If we quantify that, the redshift is quantified by looking at the difference between where the wavelength would be in a rest frame for a source that is not moving compared to where it is observed in this spectrum. So that's the difference between 1200 and 6500 angstroms. The difference is 5300. If we divide that number by the original value of 1200, we get the redshift, and that's what's indicated over there on the left hand side. The redshift is a dimensionless number, which is the shift divided by the wavelength of the light when it was originally emitted from the source object. So in this case the redshift is about 4.3, and the redshift is normally denoted by the symbol with a lowercase z. So a redshift that large means that this object is very remote. And through the Hubble law, the more distant an object is, the faster it's receding from us. This also must be receding from us at a very fast rate. We'll look at some numbers in just a short while. So I decided, is it possible to capture this particular quasar that has been surveyed by these professional astronomers? I decided to try without a telescope to see if I could get an image of it. So that's my camera with a telephoto lens. It's a 300mm focal length lens, and it's the one I use on Safari. The camera here is bolted onto this white box. The white box is a tracker, a star tracker. This particular tracker is made by the company called Ioptron. Other sky trackers are available. This is just the one that I bought a few years ago for using in the UK and whilst on holiday. The only job of a star tracker is to rotate the camera at 1 revolution per day in order that the camera can follow the stars as they move because of the Earth's rotation. Of course, the stars appear to move because of the Earth's rotation. So the star tracker has this object on the left-hand side, this little polar scope, through which you can see the North Pole. If you point this in the right direction, you can see Polaris, and by aligning the North Star Polaris up on a little reticule, you can make sure that this tracker is aligned with the Earth's axis. And then the tracker just rotates once a day, and that guarantees that the camera stays pointing at the same object, give or take a fraction of a degree. The camera is mounted onto the tracker via this little mounting here, which means we can simply adjust where the camera is pointing. This stays fixed, pointing at the Earth's axis, and the camera can point to any part of the sky that we like to take an image. As I mentioned just a moment ago, this is the same camera and lens, in fact, that I use for wildlife photography. They're not special for astrophotography, they're not customized, they're not modified. This camera and lens are precisely the same combination that I use. For instance, last year when I went on safari last summer, this is the camera and lens that I used to take essentially every picture that I took on safari. So if a camera and lens have been designed explicitly to take pictures in daylight, okay, not necessarily zebras, but they are designed to take pictures under normal daylight conditions, can the same combination of camera and lens be used to photograph a quasar at the other side of the universe? So, knowing where this particular quasar was, the people who surveyed all these quasars, of course, gave the position as well as the spectrum. So I knew that this quasar could be found somewhere in the constellation of Draco. It just so happens that the quasar happens to be close to a star. Inside this box here, which represents the field of view of the 300mm lens, that dot in the middle is a star which is close to the quasar. The quasar is not visible to the naked eye or indeed through the camera, but that star was, and so I simply lined up on that star knowing the quasar was very close to it. For those of you who know the night sky, the constellation of Draco, the dragon, is next to the constellation of Ursa Minor. This is the constellation that contains the pole star itself, Polaris, there on the right-hand side. So this particular quasar is far enough north, close to the North Pole, which means that it's very easy to see from the United Kingdom. That's one of the reasons I chose it, in addition to its distance. So having decided that's where I want to point the camera, I set up the camera on the tracker on a tripod outside my house in the driveway, trying to avoid my neighbour's floodlights, trying to avoid a street light. The easiest way of doing that was to put a wheelie bin in between my camera and the street light, such that the street light cast a shadow on the camera, and that kept the light out of the camera. And then the quasar itself was almost overhead, so the camera was pointing almost straight up. I then exposed for as long as possible, which, given that this picture was taken in the middle of July, that's not long after the summer solstice, so we have a very short period of nighttime in the UK. It barely gets dark at all, so I waited until about midnight and then started taking images and carried on until something like more than 2 o'clock in the morning. I wanted to expose for quite a few hours, but usually you don't take one long exposure because you don't put all your eggs in one basket. I took a large number of short exposures. I decided that 30 seconds would be enough, and then I just told the camera to take a 30-second exposure, and once the camera had finished taking that, it started another 30-second exposure, and it just continued doing that for a few hours. During that particular night, some clouds were rolling in and spoilt quite a few images, but rather than stop the camera, wait until the clouds had gone and then start the camera again, I simply left the camera running and then afterwards threw away all the images that were taking pictures through thin clouds or were completely clouded out. That still left me with something like 2 hours worth of data, which I added all together in ImageSXM, of course, to produce the final image which you can see there. It should be equivalent to one long 2-hour exposure. And we can see the bright star in the middle there. There's the star that I homed in on, which told me that I was pointing in the right place. That's a 5th magnitude star for anybody that knows their astronomy. But right next door is where we're interested. That's where the quasar should be. So I looked in that area. You can't see it from that particular image simply because we haven't blown it up enough. So I blew up that region, and there you can see a crop of that region, and the quasar should be bang in the middle of that image. And there it is. So that is the quasar. At some enormous distance on the other side of the universe, there is the quasar that can indeed be captured by this particular camera. Most of the light from the quasar is focused into about 1 pixel. For those of you who are interested, the diffraction limit of this particular lens is of order a few microradians, a few millionths of a radian. And that means that in principle it should be able to focus the light down to about 1 pixel. If we blow up that image, then again you can see that most of the light has gone into that central pixel of the quasar. Some of the light might be in the neighbouring pixels. Here I've exaggerated the brightness of these neighbouring pixels just so that you can see them a little more clearly. Most of the light is in the central pixel. There's a little bit of light in the wings. I've just exaggerated that so you can see it a little bit better. But essentially all of the light is focused into about 1 pixel. The camera is a 20 megapixel camera, so in other words there are 20 million pixels in the entire image, only one of which has caught the quasar in a sense. Whilst looking at that particular image, this particular chunk of sky, the sky covered by the full image that you can see in the background still, that was covering about 3 or 4 degrees of sky. But this crop that we're looking at is only about 8 by 8 arc minutes. Remember that an arc minute is 1/60th of a degree. And within that particular field that I was scrutinizing, I actually found not only the quasar, but about 10 other galaxies. I don't expect you to be able to see them, because depending on your screen, some of them might be a little bit faint, and nor can you tell the difference between a galaxy and just a foreground star, for instance, a star that would be inside our own Milky Way galaxy. But I compared this to the NASA archives to try and identify which of these blobs are stars in our galaxy and which of these blobs are galaxies way beyond our own Milky Way. And it turns out that there are something like 10 remote galaxies in this image, plus the quasar itself. So I figured that knowing the size of this particular crop, if I've caught 10 galaxies in that crop, then the total number of galaxies in the entire image is probably about 7,000 galaxies in this 2-hour exposure. That I thought was quite interesting, and you can see from the title of this slide, I've decided to call this slide the Hubble Deep Field equivalent, the Barrett Deep Field, because if you think about the Hubble Deep Field that was taken in the 1990s, the Hubble Deep Field, where it exposed for about 10 days to get its image, it caught a similar number of galaxies. It was somewhere between 5 and 10,000 galaxies in the Hubble Deep Field, and I think I've caught about 7,000 galaxies in this Barrett Deep Field, which I thought was quite interesting. Let's have a look at some numbers. I've said that this particular object has got a redshift, as measured by these professionals, of about 4. And we can convert from redshift to distance. One thing you have to bear in mind with cosmology is that when you're looking at very remote objects, very distant objects, you can't actually measure how long the light has taken to reach you. You can't actually measure distance either. The only thing you can actually measure with any sort of reliability at great distance is the redshift, because this is an observable. You look at the spectrum, you identify the lines, you see how much they've shifted relative to a spectrum that's at rest relative to you, a laboratory-based spectrum. So you can measure the redshift. If you want to deduce what the distance is, you have to know something about how the universe has expanded. Because you're looking back in time, perhaps millions, more like billions of years, if you're looking at remote objects, the universe of course was smaller, in the sense that the distance between any two objects was much smaller in the past than it is now. And if you want to know how far away that object was when the light left it, and if you want to know where is that object now, and if you want to know how long did the light take to reach you, you have to understand how the universe has expanded over the time between when the light left the object and the present day. So we know something about how the universe is behaving, but we can't be absolutely sure unless we know parameters such as, for instance, how much matter is there in the universe and what is the Hubble constant. The Hubble constant tells us that for a given distance, how fast is a particular object receding from us. In other words, what's the expansion velocity of the universe at the moment. We've got a reasonable idea of the Hubble constant, we've got a reasonable idea of how much mass there is in the universe, and hence we can draw out these curves that tell us what these distances are. But if our model is wrong, then for a galaxy with a given redshift, then these lines would change slightly in terms of the distances that they give us. So that's just something to bear in mind, that there's no such thing as an absolute relationship between redshift and distance. It depends entirely on the model of the universe we're using. Here we see I've plotted out redshifts from 0 to 6. If we were dealing with the Hubble Space Telescope, we would be dealing with redshifts possibly even beyond this. For our particular quasar, then we have a redshift of 4.3, which puts us at that particular point. And if we read off the graph, we find the distance to the quasar when the light left the quasar was about 4.6 billion light years, the blue number down here. And how long has the light been travelling? How far has the light travelled? The light has travelled about 12.4 billion years, and it's taken, of course, 12.4 billion years to travel 12.4 billion light years. We know that light travels at the speed of light, and therefore it's an easy conversion between the two. And the universe has expanded since the light left this quasar, and the quasar is now about 25 billion light years away. One thing we can note from here, the 12.4 billion years that the light has been travelling, if we take the Hubble deep field rather than the Barrett deep field, the Hubble deep field would go beyond a redshift of 4, and it would go out to probably a redshift of about 6 or 7. And that means the look back time, how far back in time are we looking with the Hubble Space Telescope, that would put us, because this green line is relatively flat, with the Hubble Space Telescope we can look back about 13.5 billion years. Whereas with my camera we can look back about 12.5 billion years. 12.5 with a Nikon camera, 13.5 with the Hubble Space Telescope. That extra 10%, that extra billion years of look back time, is basically the expense of the Hubble Space Telescope versus the expense of a camera that you might take on holiday. Let's just remind ourselves what these three numbers mean for this quasar. The blue tells us that the quasar was 5 billion light years away when the light was emitted that we caught with our camera. The light has been travelling for 12 billion years, and given that the universe is about 13.8 billion years old, that means the light that we've caught here is, or rather has been, travelling for about 90% of the age of the universe. The universe was only 10% of its current age when the light left. And because the universe has been expanding all the time that that light has been travelling to us, the quasar is now substantially further away. It's now about 25 billion light years away. And one thing you can note with some fairly elementary maths compared to the maths of general relativity is that if the quasar was here at about 5 billion light years, and now the quasar is here at about 25, then it appears to have receded by approximately 20 billion light years during a period of 12 billion years. So it's receded by a distance of 20 billion in a time period of 12 billion. That means 20 divided by 12 is more than 1. That means this object is receding from us faster than the speed of light. In fact, it was receding from us at about twice the speed of light, and it still is receding from us at about twice the speed of light. That is a very sobering thought in itself. If we have a look at the light's journey, here's a diagram which shows distance from us in billions of light years or giga light years. So there's 0 to a few gigalight years. And the vertical scale is time. So time starts at the bottom, so the Big Bang is down in the left-hand corner here, and time is moving upwards. And the quasar, when the light left, was here at the green dot, and in the top left, that's us here and now. So we can read this as saying roughly 1.5 billion years after the Big Bang is when the light left the quasar, when the quasar was at a distance of about 4.5 billion light years from us. But because the quasar is receding from us at twice the speed of light, simply because space is expanding, notice what happens to the light. After the light leaves the quasar, it actually gets further away from us. This light is trying to make it to Earth. It wants to arrive at Earth and arrive at the camera, which doesn't yet exist, but it obviously has a yearning to do so. But the light that leaves the quasar actually moves further away from us for about 2 to 2.5 billion years. The light is actually getting, if you like, dragged backwards by the fact that the universe is expanding, and so the light, for the first few billion years of its life, the light actually is going backwards and getting further away from us. Until this point where the cursor sits at the moment, let me just get the cursor back. If the cursor is there, that tells us at about 4 billion years after the Big Bang, that's the point at which the light starts to make progress and then ends up coming towards us and arrives at us 13.8 billion years after the Big Bang, something like 12.5 billion years after the light left the quasar in the first place. So the fact that the light is trying to get to us but is being dragged backwards for a substantial amount of time, a couple of billion years at least, is again a rather incredible result of its journey. If instead of thinking about the light we think about the quasar, so we know the light left the quasar here and the light is the green curve, then what happened to the quasar? Well, the quasar continued to be carried out by the expansion of the universe during the 12 billion years that the light took to arrive. And so the quasar went flying off in this sort of direction. Remember, its distance from us now, up in the top right, would be something like 25 billion light years. I've shown it as a dotted line, and more importantly, I've shown it as a straight line. Strictly speaking, that's not quite right, because due to the way the universe is expanding, the speed at which the quasar is receding from us is changing slightly. So the gradient of that line, of course, we've got distance and time here, so the gradient gives us the velocity. That should be varying slightly, so actually that red line should be a little bit of a curve, but I haven't shown it accurately. I've just given you an indication that the quasar continues to get further and further away from us, but the light originally starts to get dragged backwards and then eventually makes it to us here and now. So one way of thinking about the light's journey is to ask ourselves, well, let's just have a little bit of a thought about a narrative rather than any numbers. So the light was emitted by this quasar about 1.4 billion years after the Big Bang. And it's sobering to remind ourselves that for more than half of its journey, the Earth didn't even exist. It had been travelling for something like 8 billion years when finally the Sun and the Earth were formed within our Milky Way galaxy. And the light, of course, continued on for another 4.5 billion years or so. Life evolved on Earth from nothing through amoeba, through mammals. The light travelled on. Dinosaurs came, dinosaurs went. The light travelled on. In the last millions years or so of its journey, it finally arrived at our Milky Way galaxy. It crossed a few spiral arms and entered our solar system. In the last few hours of its journey, it arrived at Earth, travelled through the atmosphere in what must have been just a fraction of a second, hurtled towards England, homed in on the Wirral, dodged a few clouds, entered the lens and hit the camera sensor. Just a pixel in the image, but what a journey.
Yeah, very good.
So here's a photographic montage of the whole thing. There's the Barrett Deep Field as the main image, the camera that I used in the bottom left, where I pointed the camera in the top left, and in the top right a crop of the center of the image where you can see the pixel, or maybe a couple of pixels, of the quasar. So this is proof that using a camera designed to take pictures of zebras, it is indeed possible to capture the light of what I call a quasar's ancient light. Thank you all very much for listening.